Welcome to Chapter 1. The first skill set we're going to work on in this chapter is classifying real numbers. So within the real number system, if you recall, there's 5 kind of subsets of numbers that we would like you to be able to identify. The first subset is going to be natural numbers. When I say natural numbers, I'm talking about the counting numbers. So numbers you can use to count physical things that you can see. For example, 1, 2, 3, 4, 5, so on and so forth. Those would we consider natural. Again, all you can do is just count objects with them. Well, after those were created, then the idea of having nothing came into existence. So we had to expand our number system to account for the fact that you can have nothing. You can have the number 0, but then still continue with all of those other counting numbers. So when I say the term whole number, I'm referencing the ability to use 0 as well. So there's all the natural numbers, all those counting numbers, but now incorporating 0 with them. Well, after the idea of having nothing was created, then there was the idea of having less than nothing, having negative. So, for example, real world, if you're in debt, if you owe the bank money, you're going to have a negative balance. What we call that are the integers. Okay, so integers now not only have all of the whole numbers, but now all of the negatives of those numbers as well. Now, as you know, even the integers don't encompass all the types of numbers we can reference. So now we dive into the slightly more complicated one of the rational numbers. So I even have a little snippet down below to continue discussing rational numbers. So basically what a rational number is the quotient of two integers. So it's a fraction of two integers, all right? So that can lead to many different things. So a fraction of two integers means basically numbers like 1/2. Even a number like 3 would count because you could write that as 3 over 1, right? So, oh, sorry, that erased a little bit too much. So 1/2 and 3 are both good examples of rational numbers. But there are two other types of numbers that qualify as well. Rational is also going to take into account numbers like 0.125 because 0.125 can be written as 1/8. We call those terminating decimals. So any decimal that has an end to it, so zero point 0.5 or 0.75 or 0.34, any decimal that has a clear end is going to be considered a rational number. It could be written as a fraction of two integers. Another number that's included in there are repeating decimals. So for example, 0.3 repeating is the fraction 1/3. So if a decimal repeats at its end forever, just keeps going on and on and on with the same value, that is called a repeating decimal. That is also always going to be deemed as a rational number. So those are kind of the four qualifiers. Fraction of two integers, a whole number, it can be a terminating decimal or it can be a repeating decimal. Those are the four types of things that qualify you as rational. Well, the final type is irrational numbers. So irrational numbers is everything else. So by everything else, what I mean is that they never end and they never repeat. Okay, these are going to be decimals that keep going forever. They never have an ending point, but they also never end up repeating. So for example, if you look at the square root of 2, if you type that into your calculator, you're going to get 1.414213 dot dot dot. It's just going to keep going. I sometimes reference this as number vomit, okay? It's going to keep going forever, never ending, never repeating. What that means is it's never going to be able to be written as a fraction of two integers. Therefore, it needs to be of a class in and of itself. So now that you've kind of gotten brief exposure to all of these, now let's talk about how to classify them. All right, so I could ask you, which of the following numbers can be classified as integers? All right, so when we think of integers, if we look back up at that chart, Okay, the integers were all of the counting numbers were zeros and they're negatives. So if you're looking at what we're not looking for, what strikes me is we're not looking for negatives, or sorry, we're not looking for decimals. Okay, so we can use the counting numbers, we can even use negatives, but you cannot use fractions or decimals. Those would not count as integers. So what we're looking for is 4 would count. That's a nice integer. -2 would count, 0 would count, but integers do not have fractions or decimals in them. So I would not want the 0.5 or the 1/2. Rational numbers. So rational numbers, again, we're talking about things that are negative, fractions, and certain decimals, right? Terminating decimals or repeating decimals. So 5 would count as rational, right? It can be written as a fraction of 2 integers. 0 would count. Even 1/3 would count. In fact, it's the very definition of a fraction of 2 integers. Here is a terminating decimal, so that would count. Now, the issue comes in with that square root of 3. If I type that square root of 3 into my calculator, notice that is that number vomit, okay? Never ending, never repeating. So this can never be written as a fraction of 2 integers, okay? It's not going to qualify as a rational number. So I don't want to use that one. And what about the number pi? So again, if I look at pi, and I know all of you have seen this before, but if I look at pi, isn't that the same situation? It's a never-ending decimal, and it also never repeats. So this too is going to qualify not as a rational number, okay? And quite honestly, those are the best two examples. Most square roots and pi are probably the two most common examples of things that are irrational, that don't follow with all of the others. You do have to be careful though, because I would argue that the square root of 25 actually is a rational number. And the reason for that is because isn't the square root of 25 just the number 5? So if you write it in its simplest form, now it actually does qualify as a rational number. And of course, irrational numbers, well, I just kind of touched on that. This idea that most square roots would qualify, right? As long as the square root is not a perfect square, as long as it would not simplify nicely, it's going to be irrational. Or the other, always biggest example is going to be pi. So now that you've seen a little bit of how to classify them, let's talk about how to classify kind of word situations. So your school is sponsoring a charity race. Which set of numbers best describes the number of people, P, who can participate in the race? So thinking about people who could participate in that race, okay? So we could have one person participate in the race. We could have 2 people participate in the race. We could have 3 people, so on and so forth. So when you're dealing with a word situation, I would just kind of consider, well, what would make sense as a solution? Maybe list out a couple that would actually work. So let's look at some things that we don't want. So in letter C, rational numbers, we don't want fractional people, right? Irrational, again, we're not going to have decimals of people. And in B, we're not going to have a negative amount of people. So the best representation that you can have here is going to be A, the natural counting numbers. That's going to be the best representation of how many people can participate in that race. Because again, natural numbers are just the counting numbers. And that's all you need in this situation. How about this next one? If each participant in the previous example made a donation of $15.50 to a local charity, which subset of real numbers best describes the amount of money raised? All right, well, how much money could we raise? Well, any multiple of $1550. So what that means is, in this instance, we actually need decimals, correct? We need to be able to include decimals because the money amounts that they're giving include decimal values. So where's the first place in this diagram? I'll switch back. The first place in the diagram that we see decimals, well, that first place is right here in the rational numbers. So because I know that I need those, I know I have to jump all the way to the rational numbers to describe that situation. And let's look at one last example. So to calculate the circumference of a circle, you use a formula, circumference equals 2 pi r, which means 2 pi times the radius. What is the circumference of a circle that has a radius of 5 inches? So I'm going to plug 5 into that formula. So 2 pi r, which is 5. So I'm going to calculate what this actually is. So that's going to give me 10 pi. And if we type that into our calculators, 10 pi, oh, I'm sorry, 10 pi, we get 31.41592654. It just keeps going and going and going, doesn't it? So if I look at that, 31.41 inches, that number kept going, right? That pi made it as a never-ending, never-repeating decimal. So because of that, what would best describe that solution of 10 pi or around 31.41 and then just keeps going? Well, the best way to represent that would be the irrational numbers, right? That value will never end and will never repeat. So thank you for joining me for this lesson. That is going to be all. So now that you've watched this lesson, now you are ready to do the associated worksheet.